Hi dear friends, good morning to all. This is Bosep Sonani, Assistant Professor, Department of Chemistry, Arts, Commerce and Science College, Java District, Palavar. Dear friends, in the previous part, we discussed about the rotational spectroscopy, different conditions for the rotational spectroscopy. We also studied some numericals of the problem based upon the rotational spectroscopy and we tried to solve it. Dear friends, today in this part of the video, we are going to talk about the important things of vibrational spectra, which is also called as the infrared spectra. These vibrations in the molecule is because of the infrared radiation. That's why this vibrational spectra is also called as the infrared spectra. Dear friends, if we'll talk about the vibrational spectra of the molecule, then we'll come to that. It is generally observed that at any temperature, the atoms in a molecule shows a periodic displacement from their equilibrium position, and this periodic displacement of atoms in the molecule at particular temperature from their equilibrium position is called as molecular vibration. So this periodic displacement of atoms from their equilibrium position is called as vibrations. And in polyatomic molecules, the atoms are not rigidly linked with one another. These are able to vibrate from their equilibrium position, means these are able to show displacement from their equilibrium position, and the number of degree of freedom is equal to the number of coordinates necessary to locate all these vibrating atoms in the molecule in space. And each atom has 3 degrees of freedom corresponding to 3 Cartesian coordinates x, y, z. That to describe the position of atoms related to each other in the molecule. And if we we'll talk about the molecule containing n number of atoms, then there will be a 3n degree of freedom. But this 3n degree of freedom consists of rotational, translational and the vibrational degree of freedom. So only 3 coordinates are necessary to locate a molecule in space. Then the molecule will always have 3 translational degree of freedom. That's why the molecule will always have 3 translational degree of freedom. If we'll talk about the vibrating molecule, which is having n number of the atom and it is of the non-linear molecule, or it is of the type of non-linear molecule, then it is observed in a non-linear molecule having n number of atom shows 3 translational and 3 rotational degree of freedom. So this is very important. Non-linear molecule having n number of atoms shows 3 translational and the 3 rotational degree of freedom. And if you use this equation as this non-linear molecule having 3 translational and 3 rotational out of 3n degree of freedom, then from this we will be able to calculate the vibrational degree of freedom. And that's why the vibrational degree of freedom in non-linear molecule is always 3n minus 3 plus 3, means it is always equal to 3n minus 6, where n is the number of atoms present in the non-linear molecule. Non-linear molecule is in the sense is the molecule in which all atoms are not in one line. That's why it's called as non-linear. For example, non-linear molecule like a benzene, in which the 6 carbon and the 6 hydrogen means the 12 number of atoms are present. Definitely, if you put this n in this formula, so 3 into 12, that is 36 minus 6, it will have, or it will show 30 fundamental mode of vibrations, or it shows a 30 vibrational degree of freedom and fundamental bands in the IR spectrum of ethane will be, ethane has number of atom 8, so 3n into, that is minus 6 means 3 into 8, 24 minus 6, so it will have 18 fundamental bands. Similarly, in case of a linear molecule having n number of atoms possesses 3 degrees of translational freedom and 2 degrees of rotational freedom, and therefore the total number of vibrational degree of freedom in the linear molecule is given by 3n minus 5. Again n will be same, that is number of atoms present in the linear molecule. For example, linear molecule like example of carbon dioxide, n will be equal to 3, so 3 into 3 9, 9 minus 5, that will have, or it will show the 4 number of fundamental mode of vibration. As you know, just here we have, that in case of a non-linear and linear molecule, we are having the different number of mode of vibration based upon the number of atoms present in the molecule. So what are the different modes of molecular vibrations are possible? Then a molecule is regarded as the system of ball and springs, which are the bonds. Then in this type of molecule, two types of the molecular vibrations are possible. The first type is called as stretching vibration, and the second one is called as the bending vibration. Stretching vibration. In this type of vibration, the two bonded atoms continuously oscillate, changing the distance between them without changing bond angle. So here bond length may be changed, but the bond angle remains constant, and this type of vibration may be either isolated or coupled, and the coupled vibration may be symmetric or unsymmetric. I hope you can understand. Here the two bonds are simultaneously stretched. Here it is in this direction, and here this is in this direction. So this is the symmetrical stretching vibration. Here one bond is compressed and another bond is stretched. So this is unsymmetrical stretching vibration. So this is the simple case, and their stretching frequency is given by 1 upon 2 pi into c into under root of k upon mu. Mu is the reduced mass, k is the force constant, c is the velocity of light, and you know this is the very simple. While the bending vibration, in the bending vibration, the bond angle changes but the bond length remains constant. This may be of the two type, in plane and out of plane. In plane, these are again classified as rocking and scissoring. Rocking vibrations occur when the same structural or the unit or the group oscillate back and forth in the plane formed by the atoms and their bonds, and while scissoring occurs when the two non-bonded atoms connected to a common atom move towards and away from each other, just like the scissor. So this is rocking, means here the two atoms, bonded atoms, are moving in the same direction, and in the scissoring, two bonded atoms are moving in the opposite direction. So this is in plane bending vibration. Out of plane bending vibration, here this is there are two types, wagging and the twisting. Wagging means two atoms are coming out of the plane or going out of the plane in the same direction. But here in the twisting, one atom is coming out of the plane in this direction and another is also going out of the plane in opposite direction. So both the atoms are moving out of the plane in opposite directions. So here this is the types of vibration, stretching and the bending. Stretching are isolated and coupled. Coupled vibrations are again divided into symmetric and unsymmetric, while bending vibrations are divided into two types, out of plane and in the plane. Out of plane twisting and wagging, in the plane these are classified as rocking and scissoring. So this is the regarding with the different types of modes of molecular vibration. And in case of a diatomic molecule, definitely here we are not here. This is the stretching, this is equilibrium position, and this is the contraction. Both are called as stretching vibration. This frequency of vibration motion is given by the omega 1 upon 2 pi into under root of k upon mu. The stretching or compression of chemical bond results in a vibration of constant atoms about a mean position. Hence, such vibrating molecules are called as the harmonic oscillator, and their frequency of oscillation is given by this equation, and this frequency of oscillation can be converted into oscillation frequency in terms of wave number by dividing this equation by c. So we will get the oscillation frequency in terms of wave number will be 1 upon 2 pi c into under root of k upon mu, and this mu is the reduced mass, that is m1 m2 divided by m1 plus m2. So according to wave mechanics, the vibrational energy level is given in a diatomic molecule or diatomic harmonic oscillator is given by v plus 1 by 2h into omega. Similarly, this is here the important thing is that from this here it is observed that the vibrational energy levels are, though we are putting this v is the vibrational quantum number, for v is equal to 1 we are having 3 by 2 omega bar, Similarly, we are getting 5 by 2, 7 by 2, 9 by 2. And if you plot the each energy level for different values of V, definitely we are getting the equally spaced vibrational energy levels. So here, whenever we will compare this vibrational energy level with the rotational energy level, then this vibrational energy levels are equally spaced, though the value of V goes on increasing. Regarding with the 0 point energy, generally it is expected that in the zeroth energy level, the energy of the molecule will be zero. So means whenever we will put the V is equal to zero in the vibrational spectra, the energy of the molecule should be zero. But here, as this is the equation for the vibrational energy of vibrational energy levels, then this is here V is equal to 0. If we put the V is equal to 0, then we are getting this equation. It means that this indicates that even at absolute 0, when all forms of motion such as rotational, translational have ceased, the molecule will still possess some value of vibrational energy, and this energy cannot be removed even by cooling the molecule. In other words, at any temperature, the atoms in a molecule can never be completely at rest related to each other, and this 0 point energy depends on the vibrational frequency omega bar of the molecule, and hence on the strength of the chemical bond also, as well as atomic masses. So this is regarding with the 0 point energy, and this 0 point energy can be calculated here if the vibrational frequency is given. Here the vibrational frequency is 3 into 10 raised to 5 per meter. So here 0 point energy is given by 1 by 2 s omega bar. H Planck constant C, the velocity of light omega bar, is already given here, that is 3 into 10 raised to 5, and this is the 0 point energy. So the selection rule for the vibrational spectroscopy. According to the selection rule, any change in the magnitude or direction, the first condition for the molecule to show the vibrational spectra is that any change in the magnitude or direction of dipole moment during a vibration, there should be the change in the dipole moment during the vibration of the molecule should be observed, and this is an important condition. Second condition is the selection rule for the value of vibrational quantum number, just like the rotational spectroscopy. It is also delta V is equal to plus minus 1. So this is the important. And all that the molecule do not interact with the IR radiation, only those molecules which exhibit a change in the dipole moment during vibration can show IR spectra. Therefore, homonuclear atomic molecule like hydrogen, oxygen, nitrogen, chlorine do not possess dipole moment. Consequently, they will not show the vibration spectra or IR spectra. These are called like the IR inactive. But the molecules like HCl, carbon monoxide, N2, CO2 show change in dipole moment during the vibrations. So it gives the vibration spectra, and these are called as IR active. So this is regarding with the selection rule for the vibrational spectroscopy. If we talk about the combined vibrational rotation spectra, then the combined vibrational spectra, the combined vibrational rotating molecules are having the total energy is the sum of vibrational and the rotational energy of the molecule, and therefore the selection rule for the combined vibrational rotational spectra or the vibrating rotating molecule is what? Simply delta V is equal to delta G equal to plus minus 1, and delta V is also is equal to plus minus 1. So under this condition, delta V is equal to plus 1 and delta G is equal to plus 1. If the spectral lines are obtained, these are clumped together as R branch line, and under the selection rule, delta V is equal to plus 1 and delta G is equal to minus 1 transitions from another clump in the spectral line. The whatever lines are obtained, these are called like the P branch line. So for the R branch line, remember R branch line, delta J is equal to plus 1 and delta V is also delta V is equal to plus 1 and delta J is also equal to plus 1. But for the P branch line, delta V is equal to plus 1, but the delta J is equal to minus 1. So this thing can be asked to you in the final examination. So, dear friends, I think I will request you to stress the things which are that I have highlighted in this video, and this because these things can be asked to you in the examination based upon the MCQ. So here we try to discuss about the vibrational spectroscopy as well as vibrational rotation spectroscopy with their selection rule or with their condition. So dear friends, we will resume again in the next part of the video to discuss something about the Raman spectroscopy. Definitely that is quite different as compared to the rotational and the vibrational spectroscopy. So we will resume again in the next part of the video to discuss about the Raman spectroscopy. Thank you.